idea that, you know, this stuff really is all connected. It's kind of cool. And then after this, you know, like, again, I go down one path and I start thinking about all the other cool things that we could talk about. And so we'll talk about the cylindrical coordinates after this one, because that's also a cool relationship. So what I did was I included the correct, barring any additional mistakes, the correct Jacobian matrix for the spherical coordinates, the definition, you know, convert from spherical to rectangular. So what we now want to do is find the Jacobian. Right? Now, something to keep in mind, and this just kind of goes back to the idea behind a determinant. Right? So let me actually kind of take a step back here. I'm going to steal this space up here just for a sec. If I wanted to just focus on the ij vectors. All right, so here's I, here's j. All right, so vector I, vector j. All right, if I wanted to find the sum of these vectors, I could do that. You know, you find the resultant and all that good stuff. But I could also create a parallelogram out of it. Now, in this case, the parallelogram is going to be a square. Now, this square ends up being the basis for our rectangular coordinate system. All right. The I is the vector 1, 0, and the j is vector 0, 1, as we know. All right. So I can make a column, a set of column vectors out of this, 1, 0, 0, 1. All right. And so that's our standard identity matrix for the ordinary rectangular coordinate system with a basis of ij. All right, so here's my I, here's my j. All right, so I call that matrix A just for the sake of having something easier to write when I want to write determinant of matrix A, which is diagonal down minus diagonal up gives you a 1. Right? So you think about what that corresponds to, that corresponds to the area contained within this rectangle, this parallelogram, which happens to also be a square. Right? So that area, so I'll actually write area because I already used A for something else. So area of 1. All right. Now, if I wanted to perform a transformation, and let's say that transformation led me to something that was twice as long in the I direction, but the same length in the j direction. All right. So I'm doubling this dimension, but keeping this one as is. I would still have something that I could find the area of geometrically. And I would still have something, I'll call it A prime, that I could find the area of using the determinant. All right, so my new dimension, so I doubled the length in the I direction, so 2, 0, 0, 1. So the determinant of that would be, I'll just kind of cut out the fluff here, that's going to be 2, which is obviously twice as much as 1, right? So what that's giving us is a scale factor for any geometric figure in this new coordinate system based off of this transformation, right? So if I were to transform every single point in the ordinary rectangular coordinate system with I equals 1, 0 and j equals 0, 1, using this transformation matrix, then everything that I had originally in terms of geometric figures, like if I had a triangle plotted in space in my IJ, whatever that area was, it would be double in my new coordinate system, right? So what this gives us is a scale factor for area in the new coordinate system. All right, so it would be this number multiplied by the basis area in our original coordinate system. All right. Oh, okay. I'll fix that in a sec. Thanks. All right. Let's just. All right. So let me. Never thought that song would become an oldie. Or the song I'm listening to. All right. So yeah, so let's just do a quick double check down the line for this Jacobian matrix. So every entry in the first column is going to be differentiated with respect to row. So all the rows are going to zap away. So I'm just going to kind of mark it up as we go. So row sine phi cosine theta, row sine phi sine theta, and row cosine phi. So wipe all those out, each one of these. So help if I had a marker. Differentiation of the row gives me a 1. So this should be, as you said, sine of phi, cosine of theta. And we have sine of phi, sine theta, and then cosine phi. All right. So then with respect to theta, this should become a negative sign. So I got a negative sign, so that checks out. Everything else stays put. So that first one's good. Sine goes to cosine, that checks out. Everything else stays put. This one doesn't have a theta in it, so it goes to 0. That checks out. And for the last one, we're differentiating with respect to phi. So my sine phis become cosine phis. Everything else stays put for the x and the y. So cosine, okay, good. And then this cosine of phi would become a negative sine of phi. And so that checks out. Okay, so we caught, I think, the last holdout in terms of mistakes. Now we're ready to find the Jacobian, all right? So, and what we're going to get from this is, it's, like I said before, that determinant represents a scale factor in terms of area, right? So our original coordinate system is in terms of x, y, and z, all right? So that's something to keep in mind. Our original coordinate system is in terms of x, y, and z. All right. But when we're looking at a triple integral, we're really looking at dx, dy, dz. So the basis area is going to be dx, dy, dz. All right. Our transformed area in our new coordinates is going to be some sort of scalar multiple, and then our new variables, right? Because it's going to be a product of our new variables. But then in order to correct for that, in order to make it equivalent, our transformed area to be equivalent to the original basis area, there would have to be some sort of multiplier, right? Or maybe that multiplier is 1, but there would have to be something in place, right? So I know I'm going to have a d rho, d theta, d phi. d phi, d theta. Doesn't matter the order because we're treating it as rectangular in nature, right? So we'll say we did it as theta phi here, so that's what we'll do. All right. So once we figure out what that scalar multiple is, then we'll know the conversion factor that allows us to relate the spherical variables to the rectangular variables. All right. So then, this is where you kind of dive in and get down to business. We got to look for convenience. So if only we had a triangular matrix, we don't. But we do have one that has a 0 in it. So that's the row we're going to work across. So the bottom row, first entry is cosine of phi. So I have -1. We're going to use cofactor expansion. Row 3, column 1 times the cosine of phi times the matrix, the determinant of the matrix that remains when you remove the row and column containing the cosine of phi, which is going to be, it's a lot to write. So I'm going to be a little greedy. And I'm just going to do a little screenshot here. It's actually the only one I can get away with doing that because everything else is kind of split up in some capacity. So I'm going to enjoy it while I can. All right. So that's my first term. My second term, -1 to the 3 plus 2, row 3, column 2, times 0 times a 2 by 2 matrix, 2 by 2 square matrix, which you can either denote with the empty matrix, empty determinant brackets, or you can just disregard, as long as you know that the next one is going to be -1 to the 3 plus 3, and it's going to have a coefficient of negative rho sine phi if only there wasn't a typo there, it would have been a nice copy paste, but unfortunately. I'm going to resize it in a sec, so I'm just going to move this out of the way real quick. Sine phi cosine theta no, it's pretty cool, but not what I need. That looks pretty awful and exactly what I need. All right, so yeah, negative rho sine phi sine theta. Oh, I'm sorry, sine phi cosine theta. Then negative rho sine phi sine theta, sine phi sine theta, and rho sine phi cosine theta. All right, so let me do a little reduction here in size. I lost my my other 2 by 2 along the way somehow. Resize. The zooming is about to happen. All right, so now the middle entry is going to be kaput. So we're not worried about that. All this is gone. Anything to an even power, any negative number, a -1, sorry, to an even power, is going to be positive. Whether it's positive or negative to begin with, it's still going to be positive, specifically a 1. So both of these are irrelevant. So it's really just going to come down to our ability to find the determinant of these 2 by 2 square matrices. All right, so we'll start off with this guy. We have the cosine of phi Then it's going to be diagonal down minus diagonal up. And this is where, I was going to say, if I was going to screw this up, this is where it was going to happen. But as you know, I already screwed it up. This is like attempt number 3. So just keep an eye on me here. I got diagonal down, negative rho squared. All right, so far so good. I got a sine phi, a unique sine phi, a unique cosine of phi, and a sine squared theta, poor quality theta. Then the diagonal up, so minus rho squared, sine phi, cosine phi, cosine squared theta. All right, so that takes care of that one. Then from there, you know, the middle stuff zapped away. So it's going to be minus rho sine of phi. Then I need the determinant of the other. Shibiggity bangity boomity bombity boomity boom. On the fly, if you want, you see that there's GCFs galore here. So you could actually factor things out if you want and see where things go. That's up to you. I'll save it for the next step. Diagonal down, rho sine squared phi cosine squared theta, minus a negative, diagonal up is negative, minus is built in, so plus rho sine squared phi sine squared theta. All right, so we got some GCFs going on over here also. All right, so that's good news. All right, how good? We'll see in a minute. I mean, we already know how this is supposed to shake out. So lots of things better simplify. Otherwise, we're in a pickle. Nice Clausen dill pickle in your refrigerator section at your local grocery. I recommend. Anyway, so I see a common, I'll pull out a negative here, negative rho squared. I also see a common sine of phi and a cosine of phi. I'll pull those out all in one shot, all right? So I'm gonna have a negative rho squared, pulling out a sine of phi, pulling out a cosine square, a cosine of phi to go along with the cosine of phi that's already there to make a cosine squared phi. And what'll be left over would just be a sine squared theta plus cosine squared theta, which is going to go to 1 because that's a Pythagorean identity. That goes right on down to 1. All right, so that's nice. All right, so we're going to have another GCF on the other side. I'll try to show as much as I can for as long as I can. So here I see that we have a common rho sine squared, Let's pull that out. All right, so when I pull that out and group it with the rho sine phi on the outside, let's keep that red actually. I'm going to get negative rho squared, or quality negative, negative rho squared sine cubed phi, and that's going to leave me with a cosine squared theta plus sine squared theta. And that's going to zap away to 1. Because again, same reason, Pythagorean identity, sine squared plus cosine squared is equal to 1, or the commutative variation on that. All right, so I'll write the simplified form, and then you see that we have some more GCFs that can be factored out. So we have negative rho squared sine phi cosine squared phi minus rho squared sine cubed phi. All right, so GCF, I have a negative rho squared, and I have a sine that can be factored out. I can't take all of the sine cubed out, but I can at least take one factor of it. So if I pull out a negative rho squared sine phi, I'm going to have cosine squared phi plus rho squared's gone. One factor of sine cubed removed will give me sine squared of phi. Pythagorean identity. Result of 1. And so we have negative rho squared sine of phi, which if you drop the negative, because again, the Jacobian is really talking about, well, in any context, the determinant is talking about an area. The negative just implies the direction from one vector to another. So if we drop the negative here, we'd be looking at rho squared sine of phi. And so that gives you the multiplier for the variables d rho d theta d phi or d rho d phi d theta. All right, so that's actually one origin story behind where it comes from in terms of that multiplier. There's another one that honestly, every time I do it, I make a different mistake. I know it works, but I always screw it up somehow. And that is the same way that we found the derivation for the cylindrical coordinates, the r, dr, d theta. And that is take the derivative with respect to pick a variable implicitly and just work to solve, and then just limit your thetas as they approach, limit the equation as theta approaches 0. It'll work. It's not as, I'll say it's not as elegant, although some people may look at this one and say, oh, this is not elegant either, but it's definitely a lot more elegant than that other approach would be. But let me take a second and show you very quickly, but not too quickly, how this would work for cylindrical coordinates. And I'll take it as a typo, because that really should be in here also. Because I think it's just cool. All right, so we have our equations. X is equal to r cosine theta. And y is equal to r sine of theta. All right. So if I want to find the Jacobian matrix for r and theta, I would differentiate my x equation with respect to r. I got to bring that in. My handwriting is bad enough as it is. When I try to be too precise, it always backfires. Dx d theta, partials. All right. Y dr partial with respect to theta. Now this is 2 by 2 because when you're converting from rectangular into polar form, because if you remember, the z is equal to z for cylindrical coordinates. So we're not really worried about that. I mean, I could jot it down, z equals z, but that's irrelevant to the Jacobian because it doesn't have any bearing in terms of the transformation. It's staying put. So all I'm really focused on is converting the R's and thetas to X's and Y's, right? So it takes something that's three-dimensional and allows us to look at it through a two-dimensional lens, right? So when I take the derivative, the partials with respect to R, same idea as the spherical case, it's just going to be cosine sine, because the R's are just going to zap away. And for the derivative with respect to theta, we're going to have negative R sine theta, and then R cosine theta. All right. So if I want the Jacobian, all I would need to do here is diagonal down minus diagonal up, right? As opposed to cofactor expansion, trying to create a diagonalized matrix, all that good stuff. So diagonal down, R cosine squared theta minus diagonal up, so minus negative, so plus R sine squared theta. All right. Factor out the R. Probably should have led with this example now that I think about it. You end up with just an R. And so what that gives us is the relationship between dx and y, dx dy, and dr and d theta. We know that the transformed coordinates in terms of the area, we know that we would have one square that has dimensions dx, dy. What does that correspond to in polar coordinates in terms of a quote unquote square with dimensions dr and d theta? Well, it would be off by a scale factor of r. Right? So if we want to equate one to the other, that's how we would do it. Right? So yeah, you kind of look at it and say, well, this would have been nice to know back when we were deriving it previously. But yeah, but then you would have needed to know all the Jacobian stuff first. And, you know, that would have been a different conversation with the conversion of variables and all that. It's like a whole mini unit. So there's a lot going on there. There's a time and place for everything. In my estimation, this is the best time. Place, I don't know, but this is the best time to do it. All right. So let me stop that recording.